Hello. I'm not usually living in Israel, and I come here to make this speech. And also, coincidentally, I could visit DataHack, and I just wanted to know if there is here somebody who also was in DataHack. Okay, it's nice. First of all, thank you that you come, and I hope I can give you a good, something useful and interesting. And thank you, Kostya, for inviting me, and thank you, JoyTunes, for hosting us. So my name is Dmitry Dremov, and I work as a freelancer data scientist, and I also spend a lot of time participating in Kaggle competitions, mostly many years ago, like 5 years ago, but it's still having some good, so I still benefit from this. Okay. So what I would talk about is that first of all, I want to give you an idea what mean absolute error is and how gradient boosting decision trees are working. Because I was said that there probably would be some people who don't know or either know just a little about gradient boosting decision trees. So do you think that this part is important? If there is who is already knowing a lot about gradient boosting decision trees and don't need covering anything about this? Okay, so I mean, it was a good idea. Okay. Yeah, so I would say about some optimization approaches which are relevant for mean absolute error, and specifically with the gradient boosting decision trees, and about how they implemented in some popular libraries, and to show you my benchmarks, which I did in one of the Kaggle competitions, which is whereas the goal metric is the mean absolute error. Okay. So first of all, I want to start with a simple problem, just to warm up. Imagine you are in the hall and you have several elevators, and you need to find optimal position to wait. So you know that all the elevators can come, any elevator can come with the same probability. And first of all, elevators are their positions like this. And the second, you have two options. First of all, you want to minimize expected distance to walk. And the other thing you want to minimize, a guaranteed distance. So just maybe take 30 seconds to guess what would be the optimal position for both these cases. And maybe you already know, so just give a little bit time for the rest. Okay, so the answer is this. So first of all, for the first case, it is the median between the positions of all elevators. And for the last, it's just the average between the minimum and maximum positions for elevators which are presented. So, and I think that maybe the first is not that intuitive, and it's connected with the mean absolute error metric. So now I show you this graph. And this is the expected distance by the position. And if you see that it's almost the same formula, but for mean absolute error, you actually can have different predictions in different, like you can have for every point different prediction. But if you think that you have several examples and you need to predict the same value for all these examples, the optimal value would be also a median of all these of the target values. So, yeah. So I tried to come up with a couple of examples where mean absolute error actually used, and this is for sure demand forecasting, and also I know that it's used for insurance loss prediction. It might be more, but that's what I know. So I also would like to mention that yeah, so the bias for mean absolute error, and actually it's not around 0. So it kind of, you can't use it for every task, because if you need to average your model prediction or sum it for a long period of time, you can't really use it. Yeah, and one more comment on the metric is that it's very hard to understand what like mean absolute error of 10 means. So it's usually it's normalized. So if we have some data set and we're trying to measure this error, we try to normalize it on the mean target. In this case, if you have a model which just predicts in zeros, we will have exactly error of 1. And if you have a perfect model, it's still error is 0. So it is easier to understand what this means. And there is also one more connected metric, which is MAE, mean average percent error. I'm not sure. So the thing is that it is used in many cases. I actually believe that it's almost always a bad idea to use this metric, but still, if you need it, it could be optimized as the weighted mean absolute error. Okay. I think that it would be good to have, if you have some questions, I would like to answer them right now for this, the first part about the metric and the example, if you have it. Please in English. Okay. So was it all? Was it simple, or it's just too maybe too fast or too slow? So why don't have any questions? Was it too simple, so you don't need any answers? Okay. So maybe you say that it's too fast. Okay, so it's just no questions. Okay. So what about gradient boosting decision trees and regression task? So first of all, I don't want to actually give any math here, because it would be a lot of time and effort. But I will try to come up with some intuitive explanation how gradient boosting decision trees work. So it would help us to understand how the approaches I would give later also works. So the first of all, there are two conceptions: the gradient descent and decision trees. The gradient descent already knows how the gradient descent works, like in principle. Okay, so I would say that it's like 60%. So I would try to still talk about this, but maybe a little. So the gradient descent is trying to update our model weights, and by using the gradient of the loss, some loss. So yeah, I think that. So the thing is that we need to go into math to understand why this actually will lead to lead our function to represent targets, but it's still you need to understand this to understand what we will have later. So decision trees with gradient boosting use it. So who understand what decision tree is? So like for any task. So it's also about 60%. So the decision tree is trying to find regions of values where the target values are similar enough, so we can say that it's the same value. For example, we try to build a binary classifier for if the person is if some event is fraudulent or not, and we're trying to use the features about the person, the transaction, and we're trying to come up with some regions of features in the feature space which are similar enough, so we have a lot of fraudulent events there. And this is like the most important principle of decision trees. There are also some math how we are building these trees, but it's not important here. And how it's combined, and in principle, we are using decision trees, but we iteratively, instead of building tree on top of the target values, we're building it on top of the gradients near every example point. Yeah, so I'm not sure if it was clear enough, but maybe you will have more questions. Here it's important that any task, the classification, regression, even the ranking, could be solved with gradient boosting decision trees, and quite well. If it only has the gradient and also the second order derivative for most of the implementations also needed. So questions about this first part? Okay. So now I would like to talk about the optimization approaches specific to mean absolute error. First of all, how it's connected to Kaggle. I would say that in production, in business environment, it's rarely engineer has enough time to research, to try a lot of different things, just to tune a metric for like 0.1%. And on contrary, in Kaggle, the people are trying to do this research. So they're trying to be on top and like to be in the first places. By the way, are there any people here who don't know anything at all about what Kaggle is? Because I assume that, so all the people know what Kaggle is, right? Okay, so so you understand that you can put a lot of time and effort for the Kaggle competition just to try a lot of different ideas. That's why there are a lot of ideas you can find in the Kaggle forums and in Kaggle kernels. And after this, after competitions, they actually introduce it to libraries, and some engineers trying to use them. So they are, it's like a source for the real world business solutions, but just in several steps. So yeah, so I think that if you actually need to solve some task and you don't have enough ideas for this, it's usually a good idea to try to find similar competition in Kaggle and just to read through the forums. Okay, so what are the approaches I would like to mention? First of all, it is reasonable for this mean absolute error to actually have averaging by median inside a leaf of the decision tree. And this is actually introduced to the models which have this metric, to libraries. The second is there are some custom objectives which trying to combat with the so the mean absolute error has no continuous loss. So there are some objectives which are trying to be continuous and similar enough for the mean absolute error loss. And there are also approach which not changing at all how the model is trained, but it trying to transform targets so that the regular based on mean squared error optimization would actually give the same result even better. I mean, depending on the task. So for the median averaging, the most big problem is that the natural approach is to introduce it in the library. So you can't really, in a reasonable way, you can't use it if the library is not supporting it. So the good news, it is introduced in some of the libraries. And if it's not, or you don't have opportunity to use it, it could be done in a hacky way, but it would take a lot of time. So what are the custom objectives? First of all, again, we need these custom objectives because mean absolute error, if you're trying to take derivative, it's not continuous, and they don't have second derivative, and that's what every library needs if you want to use the custom objective. So in order to do something similar, similar enough for mean absolute error, but continuous, at least mostly continuous, there is a objective fair. And if you can see, it's very close to the mean absolute error if C is close to 0. So the gradient is the secant x for C around 0. And this is the second order derivative for this objective. So I wouldn't like to go through most, it's just an example of this objective, so why it's good. So the second thing, the second custom objective is TVD. I mentioned it because it is it is generally you have this distribution for demand prediction tasks, and it looks like this. So if you see your target is looking like this, then probably you need this distribution and loss and optimization, which named TVD. And the last one is Huber, and it actually trying to, also similar to FAIR, it's trying to be, to have derivative, but it is L1, it is similar to mean absolute error when error is big, and it's similar to mean squared error when error is small. So like this is by definition, and it could be introduced to library. So what are the good target transformations which could be used for mean absolute error? So the main, so what we actually want from this transformation, the most important part is that the median and the mean values are different because distribution of target is skewed. So from the transformation of target, we want to unskew distribution. And usually, it can be done for many distributions with either logarithm or power. And the parameters could be, you can try to tune them. And for my benchmark, I just took some examples from the top solutions of participants. Okay, so around this, the custom objectives and transformations, maybe you have some questions.
What is the idea behind the transformations? Why are you using them?
So let's, for example, look at the 3D distribution. Let's forget about this part. Let's just look at this part. So we have, you see that it have a long tail. So the median value would be around here. And mean value would be around here. So it would be not the same. And that's why if you try to optimize mean squared error, it would be constantly all the leaves. It would give us a little bit bigger values that should be. But if you transform target, that it would be more like normal distribution or any other symmetrical distribution, we wouldn't have this effect. So anyhow, the idea of transformation is try to transform target that it would be more symmetrical, and even the optimization of mean squared error would still give us a good result for the target.
Do you have some kind of an example of the first option?
The
Which you have that we, no. Do you have some kind of a real life example?
So as I said, if you try to build a model for the demand prediction, like if you in a shop you sell items, it could look like this. So a lot of items with the zeros, and so it is alike for the demand prediction distribution.
You have a gap between the first part and all the others?
So it could depend on the parameters, probably not, but it's still the most important part here is that we have a long peak in zero. This is the most important, and also a tail in the end. So it could be closer to, actually I don't remember the name of the distribution. So this is combination of I think. Okay, I don't even sure that it's good to add this. Okay.
So the idea is, among other things, to have symmetric distribution, right?
For the target transformation, the idea.
But then you take the inverse.
Exactly. So after you build in a model, in order to get the prediction of actual value, you need to get inverse transformation.
But then the difference between, for instance, the mean and the median will be exponentially large again. So your error will stay exponentially large.
So it is that the error would change, and that's what we want. So we want to model to be trained in a different space. So the error means something different, but we still want our predictions to be in the original space. So in order to calculate error, we still need to calculate it in original space. Okay?
Is it possible to apply any of them to classification problems?
So the question is it possible to apply to classification problems? So by design, it is considered to be a transformation for continuous values. But I just trying, maybe there is a something similar. So it's not obvious for me how you can apply the same idea for the classification. It's definitely not a trivial thing. But it might be that there are some transformations for classification problems that could be beneficial. For example, I know that there are, in some cases, we actually replacing zeros with some small values and ones with some also 1 minus epsilon values in order to get a better result overall. So it is kind of, but it doesn't need an inverse transformation, but it's still transformation of the target, which leads to a better final metric. Okay, so I think we can go next. So here, I just want to say about some popular libraries for gradient boosting decision trees and what is implemented from what I mentioned, from custom objectives and if there is a median averaging in them. There are for sure other libraries, but I'm just not that familiar with them. So for the CatBoost, there is actually mean absolute error, and it uses median leaf value. And inside, it is implemented as the quantile regression. I mean, if it's important, so we also could use any other quantile regression with any other coefficient than 0.5. So it's equivalent to the mean absolute error. It also has Huber loss. And there is a GitHub issue for the people who want to help, that there are need for more losses. And if you want, you can contribute to CatBoost something. So that just in fact. So for LightGBM, there is also mean absolute error with the proper averaging in leaf. Huber. Besides this, there is a fair objective, fair loss, and funny enough that it has in description there is a link which actually leads to a Kaggle discussion where this metric is was introduced. So, and also they have 3D loss. And in XGBoost, there is 3D loss, and also fair loss is available on Kaggle in kernel for competition with the mean absolute error. So, but it's not introduced in the library. Okay, so about this implementation part, are there any questions?
Is that possible that different leaves will have totally different distribution? Or how do you know in advance that it's going to be a specific distribution? Like some
So if you see that the general distribution is skewed, so that you can expect that in a leaf that this property is also presented, but you can't know for sure. So in Kaggle, you usually just try. So in real life, you also could try several options and see what works best.
Can you please explain again the idea of median leaf value?
Okay, so first we start with what is the optimal constant prediction for the set of target values, and this is the median value. Is this part is clear or not? This first part, like why the best constant prediction for the set of values is median value. It's not clear, right? Okay, so let's go to the graph to plot, and I think it would be easier to show. Okay, so first of all, this is the median value for these 3 dots, for 3 examples. Second, if you try to take derivative of this d distance, we actually will have signum of these differences of our position and the elevators positions. And if you actually would try to interpret these signums, is that it's a number of points on the left minus number of points on the right. And this is, so if you try to optimize this, actually would give you median value because the optimal value would be when this is around 0, the derivative is around 0, and that means that same number of points on the left and same number of points on the right. Like, now it's better? Yeah, great. Okay, so are there any more questions? Okay, so about the benchmarks. First of all, I selected a Kaggle competition, which has a big enough data set. It was around 3 years ago, and has 200,000 samples with mostly categorical features, around 100 features categorical and 14 numerical. And I did no feature engineering, which for this specific task is important, but for the purpose of benchmarking is okay. So how exactly it was done? So I tried as far as I can. I tried to use default learning parameters for the libraries, but sometimes I needed to change learning rate because either the working time was super slow, like hours, or on the contrary, it was learning rate was too big, specifically for XGBoost. By default, it's too big, so it has not enough iterations to actually learn a reasonable model. So also, it was split. I split 20% to find the number of iterations. And for the final result, I retrain it again on the full data set. It's the usual procedure which is done in Kaggle with the data set when you find in the best parameters. And the benchmark score, which is presented in the table, it's private score in this competition for the late submission.
By the way, did you use the same training? Each time you have different training?
It's the same training. So the same training set, like the same data set, and the same split for 80-20%.
Yes, of course, not the proportion, but actual data. That 80% is the same.
80% is the same always, yeah. So we fixed this the proportion, but for this because the data is quite big, it's less important. Yeah, just in principle. So the first is the transformations. I would say that first of all, the difference is significant. So if you're trying to compare, if you try to optimize just mean squared error, we get around 1,180, and if you get any transformation used, it's around 1,140, which is significant for this competition because the best result for the Kaggle in this competition is 1,100. So it is a big difference. Yeah, so for the log transformation, the constant value it was 100, and this is by one of the top competitors. He said that it was good for his result. And for the power transform, it was used. The power was 1/4. So in some sense, the log transformation and power transformation are similar, has similar shape. And also, the last row is specifically the third place of this competition said that this combination was was his best single model result. So I tried to add this also. Yeah. Here, it means that I used custom laws from the kernel, and for the rest, for just transformations, we didn't need any custom losses, any tunes. We just used the MSE over the target. And this is important because even if you don't have a tool which could use anything else but just mean squared error loss. So, for example, you use just linear regression. In this case, you still can use transformations. So you don't need to change anything inside model. You just change in the target values, and it still could give you better result. Okay. And for the custom losses, first of all, the mean absolute error for this task was better for both CatBoost and LightGBM, where they are presented from all the losses without transformations. Yeah, I would say that it is also important to remember that the best result with transformations was around the same, but a little bit better for both models. Okay, so do you have any questions about the benchmark, the procedure, and the maybe scores?
How about the time? How long did it take to?
So it really depends on the specific model. I would say that I tried for any. I have one CPU server with 8 threads, and I tried to make it less than 5 minutes. But for some runs, specifically for Huber, it was maybe around tenths of minutes. So it's not a lot, and because it's not so big, the dataset is not so big. So, and I would say that XGBoost is actually the slowest for CPU. Yeah, and it's all was run with CPU. Any more questions? Okay, so I have some conclusions on this. So just to summarize. So first of all, this benchmark was done almost without any parameter tuning, besides changing learning rate to have a reasonable time. I would say that we have more options for tuning in LightGBM. So almost all of the metrics which are anywhere used for tuning is presented in LightGBM. So for your task, it might be good to try start with LightGBM because they have more options. So target transforming is comparable, maybe even better than custom losses for this task. And I would say that the best overall result is for the either CatBoost or XGBoost with target transformation. So that's it. Thank you. If you have more questions, I would be glad to answer. And so, thank you.